Hello, everyone, and I'm sorry I can't be with you today in person, but because of a situation beyond my control, I just cannot travel to Pasadena. My name is John Ormerod, and I want to thank the organizers of this trade show, Select Global Events, for having both the foresight to recognize the need and indeed the fortitude to launch this new magnetic show in North America. Now, I'm confident this is going to be a successful event, and I'm just really looking forward to this being the first of many trade shows to come. The title of my talk today is Permanent Magnets, Myths, Misconceptions and Marketing. I've attempted to make this presentation both a little bit entertaining at the same time hoping it will be thought-provoking. Now, some of the content should be taken with a pinch of salt as my tongue is firmly in my cheek, and I apologize for those mixed metaphors. However, I may well ruffle a few feathers, so perhaps it's just as well I'm not there, so you can't confront me at the conference in person. But seriously, if anyone has any questions or you're looking for clarification, and in particular, if you strongly disagree, you can phone, email me, or video conference, and I'll give my contacts at the end of the presentation. So here are the subjects I want to try and cover today. First, a quick introduction, and then discuss several topics that fall under what I believe are myths, misconceptions, or marketing related to permanent magnets. I plan to cover a top 10 list, but due to time constraints, these are the ones I'm going to talk about today. And finally, I'm going to stick my neck out and give you my prediction of the next breakthrough mass market magnet material. So, quick introduction to yours truly. I graduated my doctorate in metallurgy or metallurgy back from the University of Manchester back in the late 70s, which, you know, when I think about it, is probably could be considered the Iron Age. My magnetics career began with Philips. I spent time in the UK and Holland and helped to develop and commercialize the first samarium cobalt 1,5 magnets, then 217, and eventually a neodymium iron boron. And then in 1990, I moved to the US and joined Arnold Magnetic Technologies, led their magnetic materials development, and was general manager for their permanent magnet businesses. In 2002, I actually left the industry and ran a metal stamping value-added assembly business that supplied primarily the automotive market. I'm co-editor of the recently published Global Permanent Magnet Industry Report and the Modern Permanent Magnets book that I co-edited with John Crote. I'm principal of JOC LLC, which is a business and technology consulting entity focused on the magnetics and metals related industries. So I kind of like to start one of these talks with what I consider to be an interesting quote. Now, admittedly, I've shown this before, but here it is with a little update. So here's a quote: "The nation that controls magnetism will control the universe." And here is a character who said it, or is credited with the quote, and that's Dick Tracy, or more accurately, the author of the cartoon strip, Chester Gould. Now, I'm guessing some of you are maybe too young and have probably not heard of Dick Tracy, but he was a very popular cartoon strip character in the 50s and 60s. Now, what's interesting to me is that this quote was made in the early 60s. And, you know, it's therefore, you know, quite prophetic since it predates rare earth magnets and certainly the Chinese dominance of the rare earth supply chain and the magnet industry. Now, perhaps today, with the concerns surrounding the geographical concentration of the magnet supply chain and critical materials, we may want to rephrase it into something like this: that the nation that controls the critical material supply chain controls their destiny. So let's move on to my list of myths, misconceptions, and marketing. And I'm going to start with what I've categorized as marketing. Now, over the last few years, we've seen several announcements about new permanent magnet materials. For example, tetratonite, samarium iron cobalt, iron nitride, and so on. And I'm frequently asked about the probability of one of these materials becoming a mass market challenger to neodymium iron boron. Now, to be honest, I don't know, since much of the relevant data and information is not available. So what I've done, I've put together a formula, or perhaps it's probably more accurately to call it a recipe, that evaluates the probability of the commercial success of a new magnet material. Now I'm calling this index P subscript CS. CS is commercial success, of course. Now, it's going to become clear as I go through this, it's not a rigorous analysis, but rather uses my 40 plus years of experience and biases I've gained in the magnet industry. So here it is. Now, it appears to be a little bit daunting, but really it's fairly simple. So let me break it down into the component elements. First, and what I consider to be one of the most important elements, is this ratio of normal coercivity, HCB, to remanence, BR. Now, in an ideal permanent magnet, we want to see a linear normal demagnetization characteristic, as shown here diagrammatically. Now, in fact, there is some empirical evidence that suggests that this ratio, HCB to BR, should be close to unity to be a mass market material. So why do I say that? Well, let's look here. So here's my estimate of the global production of permanent magnets in 2023, and I'm guessing it's around 24 billion, and here it's segmented by the materials. So what you see is that hard ferrite and neodymium iron boron account for over 80% of the market and production of permanent magnets. So when we look at some typical properties of these materials, and I'm using published data from TDK as an example. First, here's a neodymium iron boron grade, and what I've circled here in red are the demagnetization characteristics, and one can see that they're linear. The other thing I've noted at the top is that the ratio of HCB to BR is 0.96. Similarly, with a hard ferrite grade, again, we're seeing this linear normal demag characteristic and a ratio, in this case, of 0.93. Now, just to calibrate you, if you look at Alnico has a ratio of this normal coercivity to remanence of between 0.02 to a maximum of about 0.1. So again, it's a bit of an indication of the importance of this ratio, since if you look at Alnico on this chart, on this pie chart, you'll see its market share is, roughly 1%. The next factor in the formula is this thing I call price performance ratio, or price performance index. Now, it's always intrigued me that hard ferrite and neodymium iron boron magnet materials dominate the magnet market, and yet they're at opposite ends of both the price and performance spectrum. So in the past, I've proposed this simple price performance metric based on basically the price, or dollars per unit volume, of a magnet material and the average energy product of the various materials. And you can think of the index this way. The lower the price performance ratio, the more efficient is the material in converting the dollars you pay into magnetic performance. So what I'm plotting here are the dollars per cubic meter, in this case, versus average energy product of the different magnet materials. And I've drawn a line connecting hard ferrite and neodymium iron boron, which on this scale actually has a gradient of 12. Now, to me, this represents the division between what I define as niche and mass market materials. So I argue that materials with a price performance ratio of greater than 12, again on this scale, here indicated by the red arrow, tend to be niche materials, and materials with an index of less than 12, shown here with the green arrow, tend to be mass market materials. So that's the factor. The next term we have is basically maximum energy product, which I just decided to normalize to what I'm calling a typical hard ferrite grade of 4 megahertz Oersteds, followed by this term T subscript max to T subscript RT, and N subscript REC, and N subscript SC, which I'm going to define on the next slide. So here we have it. Now, since I consider the first two terms in this formula, the ratio of coercivity to remanence and the price performance index, to be the most critical, I just arbitrarily defined the constants K1 and K2 as 50. Tmax is the maximum operating temperature, TRT is room temperature, NREC is the ease of recycling this material, and NSC is the supply chain resilience. Now, obviously, those two terms are subjective, and the values are judgment calls. And I just use a scale from 1 to 10. We're basically the higher the number, the better. So I plugged in some typical values, and here are my estimates for a few examples of commercial grade magnet materials. The first is ceramic 8 hard ferrite, where we end up with an index of 142. Then 45 grade neodymium iron boron, 118. A samarium, this is a 217 grade samarium cobalt, 87. And then Alico 5 at 60. Now I got to confess, I was a little surprised that hard ferrite had the highest index. However, the conclusion one could draw is that, and then again, if you follow my argument, that for new materials to have a reasonable prospect of being a mass market material, we need to have a PCS index of greater than 100. So if you're working with new materials, try this formula and see where you fall in the index. So again, staying with marketing, it occurred to me that this concept I just explained for PCS could be extended to evaluating the prospects of a new magnetic material business startup being a success. So here I'm going to offer, free of charge to all you considering investing in a startup, a simple formula that will save you tons of time in due diligence. In this case, we're talking about a probability index I've called P subscript BS. Now, my use of the term BS is, of course, no accident. So it starts with determining the PCS for the new magnet material that we went through on the previous slide. And then simply need two documents. The first is the organization chart of the new business. And here I want to determine the ratio of process, manufacturing, automation, and tooling engineers to PhDs in the company. Now, in my view, this should be greater than 5. Now, no offense is intended to my fellow PhDers out there, but at some point the experimentation has to stop, and we need to start making this stuff and selling it. The second piece of information we need is the expense budget, or the P&L of this new business. So here I'm looking for the ratio of engineering dollars to marketing dollars. And I think that needs to be greater than 10. Now, if you think about it, a material that's really groundbreaking, marketing is going to be minimal. And I, cast my mind back to the early 80s, and I don't think Sumitomo Special Metals had to spend much on marketing neodymium iron boron magnets when they were introduced in 84, 85. So when you plug in these numbers I just mentioned, we arrive at a probability index of PBS of greater than 5,000 for a new business to be a success. So there you have it. Give it a go. Next, I want to clearly state that magnets are not falling from the sky. This is a myth. Also misquoting a phrase from a popular movie, show me the coercivity. So here I'm referring to the tetratonite material, which seems to have become the whack-a-mole of the next big magnet breakthrough. What I mean is, every couple of years there seems to be a bunch of sensational press coverage of this material. You know, here, researchers have discovered a potential new method for making high-performance magnets without the need for rare earth elements. New approach to cosmic magnet manufacturing could reduce reliance on rare earths. The material could be used to create enormously strong magnets without the use of rare earths. So some, pretty amazing claims. So what is tetratonite? Well, it's basically an iron nickel alloy that's got a unique tetragonal structure that was first identified in iron containing meteorites, over 20 years ago. Now, at that time, originally it was discovered that the structure normally only forms when cooled at less than 0.01 degrees C per year, which doesn't lend itself to commercial production very well. However, recent work in the last couple of years has shown that you can actually synthesize the compound in the laboratory using, I think they use phosphorus and boron additions to the alloy. So back to show me the coercivity, or I can show you a cheap magnet with a potential maximum energy product of 120 megahertz oersteds. The limit for BH max in CGS units is the saturation magnetization squared divided by 4. So if you take iron actually has a magnetization saturation of around 22 kilogauss. So do the calculation and you come up with a potential maximum energy product of 120 megahertz oersteds. Just to calibrate you, neodymium iron boron has a theoretical energy product of only 64 megahertz oersteds. Now, the problem with the tetratonite is that, at least from the literature I've looked at, I can only find a measured coercivity somewhere less than 2 kiloersteds. So my point is, beware of claims of potential maximum energy product. Magnetization is easy. We can find unpaired spinning electrons in different elements and alloys. However, getting those magnetic moments to align and then lock into place is very difficult. Or just to put it another way, coercivity is hard. And that may be the reason why permanent magnets are also referred to as hard magnets. So next is a misconception that I call my theory of large numbers, or beware of the claims of new rare earth deposits. So let me make this point by showing you a source of gold that's conservatively valued at around $700 trillion. So where is it, I hear you ask? Well, it's in the oceans. Now, unfortunately, the concentrations are in the single digits parts per billions. So you actually need to extract about 10 to the 18 tons of seawater to get to that gold. So here's my theory of large numbers. A ginormous number multiplied by a small number is still a large number. But again, misquoting a movie line, show me the economics. So I think this problem occurs with some of these claims for new rare earth resources. For example, here's a recent press release or article that said a mine in Wyoming could contain $37 billion worth of rare earth minerals, and of course necessary for wind turbines or electric vehicles, blah, blah, blah. However, when you look into the detail and dig in a little deeper, it seems that the concentration of rare earths, at least in the data I could find, is something less than 500 parts per million. So how much material do we have to extract and process to get 1 ton of mixed rare earth content? So here's a representation of that western US deposit. And these trucks have got 100 tons of material in each of them. Those are the number of trucks we need to of material we need to process to get 1 ton of mixed rare earths. Now, comparing that to a pretty well-known mine that's on the California-Nevada border, which are much higher grade, that's how much we have to process to get to 1 ton of mixed rare earth. So again, misquoting that line, show me the economics. The next is this ongoing myth surrounding perpetual motion devices and magnets. And I confess, I spent many hours talking to inventors who've designed some incredibly complex and detailed magnetic structures that eventually, at some point in the conversation, I have to mutter the words, "Oh, it's a perpetual motion machine." And that invariably seems to bring the conversation to an abrupt end. It appears that a lot of really smart people succumb to the belief that the laws of physics can be broken, and they're seeing a magnet being analogous to a battery that can supply infinite free energy. Now, in case you're wondering, here's an example of a 2002 US patent I discovered for a perpetual motion machine and some of the contemporary commentary. And you can see this this guy, Nick Cook, said, maybe, just maybe, March 26, 2002, when the patent was issued, will be the date I put in my diary as the day the world changed forever. Well, that quote didn't age very well. And then the inventors say here, it could lead to a permanent self-powering magnetic moment. Now, I see a magnet more analogous to a spring, although this is not a perfect analogy, but I think it's better than the battery concept. As long as you stay within the elastic limit, a spring can be compressed and then will return to its original dimension and creates work, force times distance. Similarly, a magnet operating on the linear part of the normal B versus H curve will move up and down that line depending on the magnitude of the demagnetizing field applied. But it's not a battery, it's a spring. So I can say with absolute certainty, perpetual motion machines using magnets are a myth. So, misconception. How to make money in the magnet industry. Now, based on the number of calls I receive and the interest I see in investing in certain elements of the industry, I really think there are some misconceptions. Speaking from personal experience, here are the most lucrative to the most challenging segments. So, dollars high at the top, dollars not as high at the bottom. First, become a consultant. Guilty as charged. Next, a patent attorney. Next, a trade show organizer. Now, so I'm sorry, Select Global friends, but to be honest, I don't know where you fit in this list, but I'm guessing, I know you're somewhere between the top and the bottom. Next, become an equipment supplier to the industry. Next, a distributor of magnetic materials and components, a raw material supplier, and finally, a magnet manufacturer. Again, from personal experience, it's a really tough business. You've got a lot of customer concentration, leading to low margins, and you kind of squeeze between the raw material side and the end user side of the business. Plus, the other thing to note is the level of capital investment requirement is inversely proportional to the profitability of these industry segments. So that's my view. So let's move on now and talk about the next breakthrough magnet material, at least my prediction. So I'm sure you know by now, it's been over 40 years since neodymium-ion boron magnets were introduced and commercialized. So why is it we're still waiting for the next big thing to replace neodymium-ion boron magnets? Well, discovering new materials and compounds for permanent magnets is really, really difficult. First, you've got to find a composition or phase with the right crystal structure and that demonstrates suitable intrinsic properties of saturation magnetization, anisotropy field, Curie temperature, and other things. Next step, you've got to develop a microstructure that will impede reverse domain nucleation and growth. Plus, for an anisotropic magnet, you've got to develop macroscopic texture. And finally, assuming we've solved those first two challenges, you've then got to be able to fabricate useful bulk shapes in mass production volumes. Now, for example, I've seen some interesting properties reported on things like ion implantation methods, which is wonderful if you need a few grams of a thin foil, but it's not practical for producing thousands of tons of bulk product. So, we really need to be thinking about the processes that can be readily and economically scaled up. Now, assuming all these problems are solved within this really small overlapping window, you then have to develop the extrinsic properties of remnants, maximum energy product, coercivity, the thermal, chemical, and mechanical properties. And of course, the economics of raw materials and processing has to be commercially viable. So it's maybe not that surprising. We're still waiting for the next big thing. So, as I mentioned earlier, I'm often asked what is going to be the next big thing. And honestly, I don't know, but I guess that's not going to stop me offering a few thoughts and ideas. So first, it turns out that iron is a really good magnetic element. So here I'm comparing the ferromagnetic transition elements plus a couple of rare earth elements. The third column along shows the magnetization of these materials at the atomic level, basically. And it's interesting to note, actually, the two rare earth elements, gadolinium and dysprosium, have really high atomic moments. However, the Curie temperatures are very low, which is a problem. So what I did, I took the price of each of these elements per kilogram, using the atomic weights. I calculated the silly price per atom. And that's analogous to this price performance metrics I mentioned earlier. So when you do that, by far, the most efficient element is iron in terms of converting price to this atomic magnetic moment. Now, of course, the metallurgists and material scientists and even physicists must find a way of some alloying elements that convert this BCC crystal structure to something uniaxial, and then hopefully with significant anisotropy field. Now, another plug for the importance of iron is shown in this graph. So what I'm doing, I'm plotting the market share based on my earlier market analysis versus the iron content for these different magnet types. Now, I'm going to confess that correlation doesn't meet causation, but I trust you'll admit it's an interesting trend. Basically, the higher the iron content for the magnet material, the higher the market share. So, finally, here's my prediction for the composition of the next mass market permanent magnet material. It's going to have a composition, iron, and then A, B, C, D through Z. It's going to include at least one other known element, A, B, C, D through Z. N is the weight fraction, and we need N to be much smaller than 0.4. i.e. iron needs to be much greater than 0.6 or 60% by weight. In other words, it needs to have a lot of iron in it. That's one thing I'm pretty sure the next mass market material has to be. It has to be very, very rich in iron. So here's a Dilbert cartoon that shows, like any good consultant, I believe I've identified the problem, which is, in this case, the sales are dropping. I've shown my vision for the future. We need to invent some sort of doohickey that everyone wants to buy. And then using plenty of acronyms and some really gorgeous slides, I've left the poor engineers to do the work. So I just want to finish by thanking you for your attention. I hope I achieved my goal and you found this both entertaining and it helped you to look at some aspects of the industry in a different light. Again, please, if you've got any questions, you strongly disagree with what I've been saying, just get hold of me. You can call me or email me at these addresses. So thank you, and I appreciate your attention.